Hi, my name is Ben Freiberg and welcome to the Serverless Technical Deep Dive. Serverless are many AWS services and really hard to put into 30 minutes. So today we're going to focus on the service that made the serverless concept really popular, AWS Lambda. This means we're going to, in short, discuss what AWS Lambda exactly is, as well as the different types of how to invoke a Lambda function. Then we're going to look at the execution environment and how to scale Lambda functions. And at the end, I'm going to look at some notable features and important quotas, as well as some best practices. So what is AWS Lambda? There are a few different answers to this question and a few different views. One view is let's say the high-level view. So abstractly speaking, Lambda function is code, and that code is executed when certain events are triggered, and it can do many different things. For example, interacting with other AWS services. Another view is pricing. Lambda has a very simple pricing model. You pay for the number of requests and their combined duration in gigabyte seconds. The size of the memory is configurable between 128 megabytes on the low and up to 10 gigabytes. That means, as a concrete example, a function that takes 100 milliseconds to run and has 2 gigabytes of memory configured has exactly the same cost as a function that takes twice as long but only has half the memory combined, configured. And we're going to look into a bit more detail on how you can tune this later on. So from the customer's point of view, Lambda as a service is you can upload your code or container image and you can configure your functions. This includes IAM and resource-based permissions. It can be event source mappings, but also things like versions and aliases. There are two ways to create your deployment package. So one is a zip file, zip archive or zip file, or a container image. If you use a container image, you must package the complete code and all its dependencies inside the image. If you use the option of a zip archive, you can add or configure additional Lambda layers on your functions. These are zip files by themselves that can contain additional code or data. So you can keep the size of your deployment package really small, and on the other hand, you can reuse components and share them inside these layers. It's important to remember that a function cannot have more than 5 layers, and at the end, if all the code and data is unpacked, the combined size of the data cannot exceed more than 250 megabytes for the zip file option. So let's take a look under the hood of the service. So on one side, there are these workers. These are EC2 instances on which the Lambda function actually executed in what we call micro VMs. These micro VMs contain the execution environment, which we're going to take a look at in a second. Then there is the front end of the service, which is responsible for authentication and validation. For example, it looks that the concurrency limits are not exceeded. For asynchronous requests, there's an additional service internal queue in which such requests are stored. And then there are the event source mappings, which enable Lambda to read events from different other AWS services. And that leads us to our next topic, the different invocation modes. We're going to look at how Lambda can actually be invoked, or how your Lambda functions can actually be invoked. We've seen all the necessary service components already. So the front end, which with its internal queue, as well as the event source mappings, which enable us to read from, for example, DynamoDB, Kinesis, or SQS. And these components map exactly to the three different options or modes in which your Lambda function can be invoked. So there's the synchronous and the asynchronous request, and the integration with event source mappings. And now we're going to look at each of them in a bit more detail. For the synchronous invocation mode, the caller makes a request, the front end accepts it, validates it, and if all goes well, calls the corresponding function, waits until it returns a result or an error, and this result, whatever it may be, is then returned to the caller. As I mentioned, the front end will throttle your requests if the concurrency limit is exceeded. On the other hand, for an asynchronous request, the front end, after validating, puts the request inside an internal queue and immediately returns a success to the caller, which in that case only means that the request has been successfully accepted, not executed yet. Another process then reads these events from the queue and calls the corresponding function. In case that the function returns an error, there are two more retries. So the first one is after a minute, the second one after 2 additional minutes. But if the function has been throttled or throws a system error, so any 500 error code, then the event is put back into the queue with exponential backoff of 1 second initially, which scales up to 5 minutes at maximum. Either way, at the latest after 6 hours, the event is purged from the queue. So that's important to remember that you can, for successful as well as for non-successful requests, you can define a destination, which can be an SQS queue, an SNS topic, another Lambda function, or an event bridge bus. So the last option or the last mode is event source mappings. And I've talked about event source mappings before. So what is it exactly? An event source mapping is just a resource that reads events from a source and calls a Lambda function. The use case here is that enables Lambda to process events from streams or queues that cannot call Lambda functions directly by themselves. For example, you can read events from a DynamoDB stream or a Kinesis data stream. And here there are groups of events, the so-called batches. They are read from the source and are the Lambda function is invoked with this batch. And the batching behavior varies by service, but you can tune it with 2 parameters. So one is the maximum batching window in seconds, and the batch size, so just the size of the batch or the block of events. And here the maximum batching window tells the Lambda service how long it should wait before calling the function. The batch size, on the other hand, defines on how many events a batch can contain at most. Internally, Lambda uses what we've seen before, the synchronous invocation mode. So I've talked about the different components, the different modes of invocation. Now I would like to, let's say, zoom in a bit more and look at the execution environment of a function. The execution environment is that part that runs inside the micro VMs on the worker nodes. And it's with different technologies and techniques isolated and secured. The execution environment is also responsible for the life cycle of functions. For example, the initial init phase or the shutdown of an execution environment. It's important to understand that an execution environment is only able to process at most one request at any point in time. That means if you need to process more than one event at a time, there needs to be more than or multiple execution environments. And that's how scaling works. That's also the way to understand concurrency. Concurrency is just the number of execution environments that are working on any request at a point in time. Let's give an example here. Here we do have two execution environments. So the first one, the first request looks at if there's any execution environment already present. There is none. So it triggers the provisioning of the first execution environment. Inside, the initialization is happening. That means the code is being downloaded. Any optional extensions are initialized. The runtime is initialized. And after that, the initialization code of the function itself is triggered. So that's the code outside of the handler. Then, after all this, the function is ready to accept requests to be invoked. And if at some point in time there comes another request, while all the already available execution environments are busy, another execution environment is provisioned. And if an execution environment hasn't been invoked for a specific time, then the shutdown phase is triggered. That means the runtime as well as the optional extensions are terminated, and then the execution environment itself is removed. So let's look on a bit more into detail between managed runtimes, custom runtimes, and container images. So in case of managed runtimes, so runtimes that the AWS Lambda service manages for you, you just need to provide your function code as well as any optional extensions. Meaning you provide really just your business logic, the handler, whatever you need your function to perform. If you, on the other hand, use custom runtimes, you need to include that runtime as well as the code. And again, optional extensions. And on the other hand of the spectrum is a container image. Here you need to include everything from the container image, the function code, and any optional extensions. So the runtime API is the only way to communicate with your container image. I've mentioned before that the runtime might depend on the configuration of your function, meaning that you have you can scale the memory of your function from at the minimum of 128 megabytes up to 10 gigabytes of memory. And there's a proportional increase in CPU resources as well. That means it's possible that a function that has a higher memory configured might actually run a lot faster. So there's a really nice tool that tries these different configurations and visualizes them and enables you to find really the sweet spot of the configuration where your overall execution costs are minimized. And that ties in nicely to one of our recent additions. So since September last year, there's the possibility to run your Lambda functions on our ARM-based Graviton 2 processors. Why would you do this? So we've seen over all our customers that there is on average up to 19% better performance. So your code just performs better. And you get an additional 20% lower costs because your runtime, the duration of your functions is shorter. But it's important to keep in mind that your code or binaries especially need to be compiled for the ARM64 architecture. and that some libraries or tools might not yet be optimized for ARM yet. So it's important to do your own testing to compare these objectively. We've talked about scaling a bit before on how if there's multiple requests that multiple execution environments are needed to respond. But how does scaling really work? And there are two important, let's say, quotas to keep in mind. One is the account concurrency. That's the maximum concurrency across all your functions in a given region, which can be increased. So that's a soft limit. On the other hand, there's the burst concurrency, which is the maximum increase in concurrency for the initial burst of traffic. So let's imagine you have a Lambda function that just performs one or two invocations at a point in time. And then there's a huge influx of traffic due to some external events, some sales, some whatever it may be. And depending on your region, the service is able to scale up to, let's say in Ireland, for example, 3,000 additional execution environments immediately. That depends on the region, as you can see. And after that, regardless of the region, the Lambda service will scale by 500 additional execution methods or additional concurrency per minute. So there's a linear increase after this initial burst limit. So let's give an example. Let's see here. So we have a function that has, let's say, a very low amount of concurrency, and then there's a high burst in concurrency. So up to the burst limit, the Lambda service will scale your functions immediately. After that point, there's only going to be a linear increase of 500 additional execution environments or additional concurrency per minute up to the concurrency limit of your account. And again, if the traffic subsides, we've seen that the execution environments are then removed over a period of time. So what happens if you use provision concurrency? So provision concurrency means that you tell the service to keep a specified number of execution environments ready or pre-warmed to reduce this initial this initialization process of downloading the code, performing initialization, potentially costly initialization of let's say database connections or anything else. So you have this pool of pre-warmed execution environments. So what happens is if your traffic is within the requested provision concurrency, the service is able to scale immediately. After that, again, you are limited by the standard concurrency increase, so 500 per minute. On the other hand, there is reserved concurrency, which means it's a limit of how much concurrency a given function can use. So here for an example, let's say I have an account limit of 1000 and I've allocated 100 reserved concurrency for each to my function dev and my function prod. So these are only able to scale up to 100 and they will be throttled if there would be a further increase in concurrency. In addition, it means that all my other functions in the account in that region can only use the remaining 800 concurrency. So it takes away, let's say, the reserved concurrency from the account quota. Now I would like to spend or look at a few notable features that I think are very, very useful and very important. So one is the Amazon RDS proxy. There's a typical challenge with Lambda or serverless architectures where if you have a function that scales very highly or have a lot of throughput and you need to connect to a database, it's possible to overwhelm the database with connection requests. And that's why Amazon RDS proxy exists. So it sits in the middle. So your Lambda functions don't connect to the database directly, but connect to the RDS proxy. And the proxy keeps, let's say, a pool of long-running existing database connections to the database. And whenever a database connection request or database request comes in from a Lambda function, it will look at the existing database connections it has and use one of these to perform the task for the Lambda functions. So you can really pool your connections at that point. One very recent addition to Lambda is the increased ephemeral storage. Previously you were limited to 512 megabyte of local storage. So that's let's say a temp folder. But we've seen with customers that process or that have data intensive workloads, for example, creating PDF files or ETL jobs or media transcoding, for example, that really require fast, scalable local storage to process the large amounts of data quickly. That they need a larger ephemeral storage because the ephemeral storage is reused in subsequent executions of this execution environment. So you don't need to download it every time. And that's why we now offer an ephemeral storage up to 10 gigabytes. We've talked about quotas, some quotas before, but I wanted to really put the most important one, in my opinion, on one slide to really highlight them, especially the hard limits. So we've seen the burst capacity varies per region, but it's a hard limit. Another hard limit to keep in mind is the invocation payload. So the size of the payload that you invoke your Lambda function. That varies by mode. So for an asynchronous invocation, it's up to 6 megabytes, whereas for an asynchronous invocation, it's 256 kilobytes. If you need your Lambda function to process more data, there's, for example, the option of putting the data in S3 and just giving the pointer to the data to the Lambda function. Also, I've mentioned the maximum size of your deployment package, which is for, let's say, the zip file variant, including your layers, 250 megabytes if it's unzipped, and your container image. And if you have larger deployment package, you could look at container images, which can be up to 10 gigabytes in size. It's also important to understand the difference between the concurrent executions, which can be increased to hundreds of thousands if necessary, and the invocations per second, because you can have a higher number of invocations per second than your concurrent execution quota. You need to understand that if you have a sustained number of higher invocations per second than your concurrent executions, that at some point you'll probably be throttled. And that again, that varies if it's a synchronous or an asynchronous invocation. So there's a lot of best practices around Lambda, and I'm going to share a few of them and provide you with additional resources. I've got 3 topics. The first one is observability. And this includes, for example, tracing you could use AWS X-Ray to really give you an end-to-end view in the execution of your function in order to, let's say, understand or debug which parts of your function are taking really long, where any bottlenecks are. Is it a database connection? Is it some I/O processing? This gives you the insight into this really detailed, fine, granular execution timeline. Another best practice is to use structured logging so that you can enable any search and aggregation use cases later on, and to use custom metrics in addition to the metrics that the AWS Lambda service already emits, and ideally use the CloudWatch embedded metrics format for that. All this and much more is actually bundled in the Lambda Power Tools library on GitHub, which not only exists for Python and Java, but also there is a new beta for TypeScript. The second topic is error handling. And as we've seen, you need to differentiate between the mode of invocation. But overall, it's important to configure either, let's say, a destination or a dead letter queue, at least for the failed invocations, so that you're able to redrive them, to reprocess them once you fixed your issue or your bug. The last one is optimizations, function optimizations. And there are two main things to keep in mind. So on the other hand, you should strive to keep your deployment package as small as possible. So only include the dependencies that are really necessary. This, for example, leads then to faster initialization times, to a faster time to the first request. And it also makes iterating or developing much easier. On the other hand, you need to remember that execution environments are reused, so that you put any initialization code outside of the handler, because the handler is invoked every time the function is invoked. So, for example, make database connections outside of your handler, or download any necessary data outside of your handler. So in closing, what we've seen now, we've seen that Lambda is on a high level a way to put your code, to enter your code and trigger its execution via events, either actively by an asynchronous or synchronous call, or by enabling the Lambda service to read events from other services on your behalf with event source mappings. You can put your code directly into the service using managed runtimes, so you really only need to put your business logic into it. You can use custom runtimes if necessary, but you can also bring your container images if you have the requirement for, let's say, a large deployment package, or if that's what you're more familiar with. And then your code and your function can do whatever you want. For example, integrate with other AWS services, but anything you want to do. Here are a few more resources that I've mentioned, or that are very helpful for developing and managing Lambda functions. So that's all from my side. Thank you.